So, good afternoon, everybody. Exam time is nearing, so people start to stay awake. Which brings me to the question, who of you would participate in an exam? Because I'm still thinking of having the exam either orally or in writing. And of course, the more you are, the more probable it is that we will have a written exam. So that's on the order of 10 people. Right? No, just a week. No, because I'm not sure whether we're going to write it or whether we are going to meet for oral exams. And then, okay, good. That gives me an impression. Now let me think about this. All right. Last time we spoke about perturbation theory. And the main point was to develop, at one particular example, how you would proceed in order to set up perturbative terms. And we saw that can expand our exponential interaction operator into a power series and describe all the elements, or all the terms in the power series in a diagrammatic way, which then allows to systematically construct all the terms that you need. And there are very many of these terms, and I told you that there are computer programs for doing that, and that the main point of discussing that was to show how you can proceed in a perturbative way, how you can include the particle interactions in a perturbative way. Do you have any questions about these things? Not the case. And now for something completely different. Remember, we discussed already a universal property of structure formation in Gaussian random fields, and that was that the eigenvalues of the deformation tensor that ultimately gives rise to the compression or expansion of structures, the probability distribution of the eigenvalues of this deformation tensor is such that equal eigenvalues are forbidden. And this gives rise to the frequent examples of filamentary or network-like structures that you can observe everywhere in nature, and among them also in cosmology. Now I would like to come to another universal property that we have found in cosmic structures, that has to do with the small-scale behavior of cosmic structures. So in other words, the point that I would like to address today is an exact result on the small-scale, nonlinear, but free cosmic power spectrum. I want to see how that power spectrum behaves asymptotically for very large wave numbers. Right? So the idea is, anybody need help? All right. The idea is to look at the power spectrum and to see whether we can make any rigorous mathematical statements about the behavior of that power spectrum for wave number k to infinity. That's the point. That's what we would like to address. Now, as we go along today, I will need lots of ingredients. Let me put the ingredients everywhere so that I won't have to interrupt the main line of thought while we are going through these things. So first of all, what we will look at is this curly P power spectrum that we discussed a number of times already. That will be the main focus of attention. I'm going to write as an argument only the wave number k, because that's the only relevant argument that we are going to need. And we saw earlier that this is an annoying Gaussian damping factor that we would like to understand better. And then an integral over a three-dimensional separation vector r of exponential of minus t squared k squared some function of r. I'm going to write this out. And the Fourier phase. That's the object of desire for today. That's what we are going to look at. Now, what was this function f of r? That, of course, has to do with our momentum correlation functions a1 of r and a2 of r. And I think you remember those, do you? They appeared so free. All right, that's what we are going to look at. And remember how we derived this. We set up the free generating functional for KFT, then applied two density operators, and that was what came out. That's the thing. Now, that's the free nonlinear power spectrum. All right. Later, we are going to need another, or it will be advantageous to use another representation of this function f of r. And remember that came by evaluating a quadratic form containing the momentum correlation function or correlation matrix. And I'm going to write this in this way. Minus k squared times f of r is transpose wave vector k, momentum correlation matrix CPP times vector k. I'm writing it in this way. Well, just because to isolate the k square factor here, because we are later going to investigate the asymptotic behavior of this curly p function as k goes to infinity, so I need to separate the k from the f of r. I'm assuming that you remember how this came about. Right? It's the quadratic form of the wave vector with a momentum correlation matrix, and then remember we split the correlation matrix into a contribution parallel to the separation vector r and perpendicular to it, and this is how the functions a1 and a2 came about. All right. Assuming that you accept that, finally, there's the equation for the momentum correlation matrix, and this was the integral over k prime tensor multiplied with k prime times the power spectrum of the velocity potential p psi e to the I k prime times r. And r is the separation of the two momenta that we correlate. All right. Remember, psi was the velocity potential of the particles. And so if we correlate initial momenta, we have to take it to the derivative of the velocity potential. And this is how these two vectors, k prime, their tensor product comes about. Okay, are you willing to accept that? That's the basis of what we are going to look at. Now, this is the physical part. Now we need some mathematical part. The mathematical part will contain a number of things. And among other things, there will be a gamma function. And we are going to need to evaluate gamma of n plus a half. n are integer numbers, positive integer numbers. So we need half integer gamma function of half integer. There's a formula for that. All of these values go like square root of pi, and the prefactors are n minus 1 double factorial. That's particularly loud. Divided by 2 to the power of n times root pi. This is how it is. Okay, I'm going to need that later. Then I'm going to introduce a multi-index. This is to save notation. The multi-index will be a combination of d indices, where d is the number of spatial dimensions that we are dealing with. So I want to write things like alpha as a multi-index, which is a d tuple of indices. And d is the dimension of the vectors r and k and so on that we are going to deal with soon. Okay. This is just a safe talk. Do not strain anybody's patience by too much. Then we are going to use symbols like alpha, absolute, the sum over all indices contained in the multi-index. I'm going to use a factorial for alpha, and that's going to be this expression here. So it's the product of factorials of the indices. I'm going to use things like this. Where mu is another d-component object. And what I mean by that is this. I'm just fixing notation. There's nothing mysterious going on. And I want to use gamma of alpha, the gamma function from above, and the multi-index alpha, by which I want to understand the product from J to D over gamma of alpha J. All right, this is just the multi-index notation that I'm going to use. It's going to be convenient as we move along. I also want to use an alpha order derivative d alpha, by which I'm going to mean d to the order of absolute alpha. Now, d alpha 1 like this. You see what I mean? There are going to be d coordinates. And I'm going to take derivatives with respect to all these d coordinates, each one to the power of alpha d. Sorry, power of alpha j, to the power of all the individual index components of the multi-index. Okay. Yes.
Does the m plane, the alpha plane, that alpha plane, the take to the power of alpha j is not enough?
That's true. That's true. Yes. This is, yeah, as you say, this is an exponent, not a superscript. All right. Good. Now, with this notation at hand, let me formulate a problem and the solution. And the solution to the problem comes from a theorem from mathematics that I'm not going to prove. If you want to look it up, find it in the book. If you want to know the book, I can tell you. But for the moment, I'm just going to accept that. The point is the following. Yeah. Because I made a mistake. Thank you. All right. Suppose you have an integral like this. It's a d-dimensional integral over some domain omega in Rd. It's an integral over something, namely an integral over this expression here. And I'm going to say more about what these functions f and g are supposed to be like. So omega is an open domain in Rd, and it can be Rd itself. I'm carrying out a d-dimensional integral over this product of functions here. Now, the point that I'm driving at is Laplace's method, which says the following. Suppose f has a global minimum somewhere. Then this minimum here, because of the exponential decay of this prefactor here, this minimum will dominate the complete integral. So then, this allows me to make a statement about the asymptotic behavior of this integral, because then I can factor out this exponential here taken at the minimum of f and develop the rest of the integral into a series. And it turns out that asymptotically for large lambda, asymptotically for large values of lambda here, this integral goes like e to the minus lambda f of x0, where x0 is supposed to be the location of the global minimum of f, divided by lambda to the power of d half. And now comes a series of coefficients Cn divided by lambda to the power of n from n equals 0 to infinity. And of course, I will have to tell you what these Cn's are, but that's the point of what we are going to look at. We will try to apply this theorem, which is not complete yet, of course, because first of all, I didn't say anything about the conditions, and then I didn't specify what the Cn's are. But this theorem will allow us to make statements about a more specific case of this type of integral. Namely, I'm claiming that once I have this result from mathematics here about Laplace's method, and I want to consider now what we call Fourier Laplace integral. Again, that's a d-dimensional integral over open domain omega. Now I'm taking the same exponential prefactor, e to the power of minus lambda of x. And now for the function g of x, I'm taking Fourier modes. And then I'm claiming, you see there's obviously some intimate relation between this expression and that one. So I want to use general mathematical statement about Laplace's method on Fourier Laplace type integrals that I want then to apply to our nonlinear free cosmic power spectrum. All right, the claim is that I can derive from that this integral, Fourier Laplace type integral, is asymptotically of the form e to the power of minus lambda times f of 0. Now I'm assuming, without loss of generality, that the minimum of f is at x equals 0. In other words, I'm just shifting my coordinate system such that its origin is at the minimum of f. All right, divided by lambda to the power of d halves, square root 2 pi to the power of d times the determinant of some matrix A. Of course, I will have to tell you what A is. Now, exponential of minus k transpose A to the minus 1 k times 2 lambda. All right. So the program for today is, first of all, to accept that, to specify the Cn, then to apply this result to this type of function, and then to specialize this result to that kind of power spectrum. All right. Now about the notation. I'm assuming that F and G are both from this. Well, I shift the coordinate system such that the global minimum of F is at the origin. So F of 0 replaces F of x of 0, F of x0. All right, so I'm assuming that F and G are both functions from C infinity on omega. For simplicity, you can relax this assumption, but we are just assuming that they are smooth functions on omega. Then another condition I already said, namely that F is supposed to have a global minimum at x0, or in the application to the right, at x0 equals 0. Then I'm assuming that the Hessian of F at the global minimum, and this is the matrix A, that this is positive definite. Otherwise, I'm a poor guy. Sorry. What else? Yes, and I'm assuming that J is absolutely convergent. The integral J is absolutely convergent. All right. So let me write down here A is the Hessian of F. I'm going to write this as the matrix of second order derivatives D2 of F taken at 0. It's the Hessian of F evaluated at 0. And of course, one of our jobs towards the end will be to work out what the Hessian of this function F is over there. All right. Good. Later we are going to need the eigenvalues of the Hessian. And since the Hessian is symmetric and real, all these eigenvalues are going to be real numbers. And I'm writing them as I'm going to write them. Okay, the eigenvalues of A are supposed to be mu1 to mu d. They are going to be the mu's that appeared over there. All right. That's the set out of the problem. Are you with me? All right, now I have to tell you what the CNs are. Cn is the sum over all multi-index configurations whose absolute value is 2n. So I fix an n because I want to look at the order n in this asymptotic expansion. Then I'm looking at all combinations of entries in the subindex such that the absolute value of, all entries in the multi-index, such that the absolute value of the multi-index equals 2n. Then I need a kind of Kronecker symbol for the multi-indices, which I forgot over here. Delta of alpha, that's going to be 1, 0, as we expect from Kronecker sum be 1 if all the subindices are even. So alpha even for j 0. So in other words, this delta over here is out all configurations in which all subindices are even numbers. All right. Then we have 2 divided by u to the power of alpha plus 1 by 2 in the multi-index notation that I sketched here at the board over there. And gamma, the same argument, gamma alpha plus 1 divided by 2. And then p alpha is another function, capital T. I'll tell you what that is at 0. That means the location of the minimum of function f divided by alpha factorial. Okay, these are the coefficients here. Yes, the mu's is, yeah, exactly. In the same multi-index notation, the mu is the collection of all eigenvalues of the Hessian of f at minimum. Yes, in this way over there. And so mu or 1 over mu number. We are not dividing by vector, right? But we are dividing by a product of numbers. Right? So in this sense here, I mean this notation. All right. Now what the hell is G? It seems endless. It means mu from H in the following way. I'm looking at an environment of the location of the minimum of f. And then I'm introducing a diffeomorphism H that maps this environment to some other environment in which instead of the coordinates x, the coordinates y are running. In other words, I'm introducing a new coordinate system in the vicinity of the global minimum of f, such that I can write f in this way here on this environment of x0. This is f of 0 plus some quadratic form. And I know that such a diffeomorphism H exists from Morse's lemma. So Morse's lemma ensures that such diffeomorphism H exists. In other words, I can introduce a coordinate system in the vicinity of the minimum of f, such that f does in fact become exactly parabolic. All right. Now, once I have this diffeomorphism H, I introduce the function capital T such that g of y is g after H the same diffeomorphism to remap the function g, and then I have to use the Jacobian this diffeomorphism here. Okay, so far so good. Now we have all the symbols complete. And as I said, Moses' lemma ensures that such a diffeomorphism exists. But now we know a bit more about this diffeomorphism, right? Because we know that in the immediate vicinity of f of 0, you can approximate f if you replace this quadratic form here by x transpose times a times x transpose, where a is the Hessian of f. Right? And in the immediate neighborhood of the minimum of f, those two representations must agree. So in other words, I do know that the matrix Q that the matrix Q is given by H0 transpose times A times H0, where H again is the Jacobian matrix, but now H0 is the Jacobian matrix taken at the minimum. Okay. All right. And I know that the determinant of H taken at the minimum must be the determinant, must be 1, right? Because if I introduce the original coordinates x, then I must be able to write this as x transpose times Hessian times x transpose around the minimum. And then the Jacobian of the determinant of the Jacobian at the minimum must be 1. And this means that Q must be related to A in this way. All right, so far so good. Yeah, and if you wanted to evaluate all these CNs, then once you know the function small g, then you can proceed. But we do know the function small g. If we now go to integrals of the Laplace Fourier type, we know that small g is just given by the Fourier mode. All right. So let me maybe where do I wipe off what? No, still need too much of that. So this is the end of the general introduction here. Now let us specialize these results and expressions and so forth for g equals e to the I kx. Yeah. That's true. That's true. So this, yes, that's what is understood, right? So yeah, what you're saying is that we are arranging coordinates y such that y of 0, y of 0 is 0. Huh? Well, I want to map the origin of the x coordinates to the origin of the y coordinates. Then I know that the minimum is also at y equals 0, and then I evaluate the Jacobian at this point. So that's what I should have written here. Okay, that's true. Okay, so this is now for Fourier Laplace type integrals, the function small g. So the function capital G is given by e to the power of I, k, times h of y, times the determinant of the Jacobian. That's our function capital G. And now we can insert our function capital G in here and see what happens. And this is going to be really great fun, right? As you can imagine. All right, so now we need to apply an operation like this to this function G. I don't want to do this. And I don't need to do this. You see, of course, I would have to use the product rule at every order of the derivative. And then the whole situation becomes clearly very messy after a short while. Bell polynomials show up where you don't like them and so on. However, we are not interested in the complete derivative, but we are interested in the highest powers of k in this derivative. Because ultimately we want to drive k to infinity. We want to see what happens to these derivatives here if k goes to infinity. So I only need to know the highest powers of k in this derivative. And I will get the highest powers of k if I apply all of these absolute value of alpha derivatives to the exponential factor, not to the rest. So asymptotically, for k to infinity, this will be d alpha e to the I k times h of y, evaluated at y equals 0, times the determinant of h evaluated at y equals 0, which is 1. Okay, now this is an easy task. This is an easy task because any derivative will bring a factor of k times vector k here times the respective derivative of our diffeomorphism down. And then a phase factor will remain. But ultimately, I will insert h of y at y equals 0 into this phase factor, which will set the phase factor to 1. So all I need is the following expression. This will be I k t, the transposed wave vector k, now times matrix H0. Of that, the jth component raised to the power of alpha j. And I will get a product from j equals 1 to t. Do you see how this happens? Suppose you go with this kind of operator to this phase factor here. The first derivative will take the factor ik down times the derivative of the diffeomorphism with respect to the component j of y. And since I'm doing this alpha j times, this will happen, or this will be raised to the power of alpha j. And this will be repeated for all the coordinates j. All right? Yes. Now, this is, as I said, yeah. Yes, that's true. Everything to the right of the symbol here is asymptotic for large k. That's true. So this is not an exact expression, of course, right? This is an expression that is true if k goes to infinity, or in the limit of k to infinity. But that's all we need for now. Okay. Now let me use all of that in the expression for Cn on the backboard. Cn equals sum over alpha equals 2n. Now remember, this Kronecker delta here picks out all subindex combinations only which are even. Yes. These are all combinations of subindices that sum up to 2n. No. Look, they are enumerating the coordinate directions in the d-dimensional space that you're looking at, right? Like here. You mean the range of values of all they're positive integers. All right. Now I'm going to expand symbols that still appear in multi-index notation. This product here. And the product now allows me to write 2 divided by uj. Remember, the mu j are all the eigenvalues of our Hessian. Alpha j plus 1 divided by 2. Right here, I'm just writing out what the multi-index notation dictates. Then I have gamma of alpha j plus 1 divided by 2. And then I have I kt h0 component j raised to the power of alpha j divided by alpha j factorial. So now I have just expanded the multi-index notation. The I also needs to be raised to the power of alpha I. All right, and now you see this combination here of this sum of absolute alpha equals 2n and the Kronecker delta here ensures that all relevant multi-index components alpha j must be even numbers. So it's much more convenient to introduce a new multi-index n. I think there's little risk of confusing that. Which is just half of the alpha. Okay. So this is sum over all multi-index combinations whose absolute value is n. Yeah, come on. Now I can get rid of this, right? Because all the odd combinations drop out anyway, and we have only even combinations left. Product J equals 1 to D. All right. Now 2 divided by mu j, nj plus a half gamma of nj plus a half I kt h0. Let me ignore the I for now. To the power of 2nj. And now I can write minus 1 to the power of nj, right? And here we have 2nj factorial. Now, of course, this makes life a lot easier. Let me now use one of the results that I already envisaged over there. That's nj minus 1 double factorial divided by 2 to the power of nj times square root of pi. Now let's have a meditative look at what's still left. Look, here we have 2 to the power of nj, but also 2 to the power of a half. The 2 to the power of a half will appear in all these products, so I can pull it out. I will get 2 to the power of d half. Same with the square root pi. So we'll get square root of 2 pi to the power of d. I can pull this out. Now I have the nj minus 1 double factorial, 1 times 3 times 5 times 7, divided by 2 nj factorial, 1 times 2 times 3 times, and so on, forward to nj. If I divide this double factorial by this factorial here, 2 to the power of nj times nj factorial is left. Look. It's a double factorial. That's the factorial. So you see that the double factorial cancels all the odd factors in here. So what is left is just 2 times 4 times blah, 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 times 2nj. And this is 2 to the power of nj times nj factorial. So, A. This one, together with that one, is just going to leave this combined expression here. How nice, right? Because we have a 2 to the power of nj in the numerator. Now also in the denominator. And it's going to be gone. Then we have another 2 to the power of nj over here. Right, that we have to divide the whole factor by pi. But we also have a minus 1 to the power of nj, so we have a factor of minus a half to the power of nj. That's how it should be. Nj minus 1 double factorial. But that's how it is defined, right? I mean, you well, of all the numbers that are left, I can factor out a factor of 2. No. Suppose I go up to 7, right? Then Nj would be 8.
So from 9, 11, 13, 15.
True. I think that is wrong. That's what fixes this. Yes. Are you looking this up, Fabio? I think that's fixed in this way. Yes. Thank you. You make me sweat here. Huh? Okay. No, great. All right. What's left? Another thing that's left is that we have the mu j here, all to the power of a half. So we have a product of all the mu j's raised to the power of a half. But the product of all the mu j's is a product of eigenvalues of the Hessian. So that's the determinant of the Hessian. So and I should have written that this is the asymptotic expansion of the Cn there. All right. Now we have 2 pi to the power of d divided by the determinant of a and the whole thing taken the square root. Now we have the sum over all subindex combinations here. Now what is left? We said that 2 to the power of nj cancels one of these, right? Either that or that. Then one of the 1 over 2 to the power of nj we combine together with a minus 1 to the power of nj, and we get minus a half to the power of nj. Okay. Then we have kth0 j squared to the power of nj. We have 1 over nj factorial. And we have mu j to the power of nj left. And this is complete now. Right? Now we have taken care of all the factors that we had. Now let us have a look at this particular expression here. First of all, I can write kt, k transpose, times h0, jth component, squared, divided by mu j. I think I need to take the complete expression here. So this sum here will be minus 1/2 k transpose times h0 times mu j to the minus 1 times k transpose times h0. I'm intentionally pulling these apart to the power of nj divided by nj factorial. Now I claim that this is I'm getting this expression. What I'm driving at is the following. These are the eigenvalues of the matrix A to the minus 1. This is the vector times a vector with these eigenvalues in the middle. So this corresponds to vector K transpose. Now together with these matrices H0 times the matrix A to the minus 1 times the vector K. And what I'm claiming is now that this is 1/2 K transpose A to the minus 1 times K to the power of n divided by n factorial. And believe it or not, this turns out to be true. Right? So in other words, I can combine these terms now such that I can write them in this way. And I'm using that, the diffeomorphism H, or rather its Jacobian determinant, times the matrix Q that we had in Moses' lemma. Must be the Hessian. All right. So if this is the case, then I can finally write that the CNs are asymptotically given by the prefactor that we already had, two pi to the power of d divided by the determinant of A, Now times minus a half k transposed a to the minus 1 times k to the power of n divided by n factorial. And now you see what happens if you now sum over all. You now sum over all the CNs. For these Fourier Laplace type integrals, then you find that they asymptotically go like e to the minus lambda f of 0 divided by lambda to the power of d halves. Now sum over square root 2 pi to the power of d divided by square root of that a. Now minus a half kt a to the minus 1 times k to the power of n divided by so in the original expansion we had lambda to the power of d half plus n. So since I'm factoring out lambda to the power of d halves here, lambda to the power of n remains, and I need to divide by n factorial. And now you see this just sums up to the exponential, and we have this prefactor here. So this means that we have an asymptotic expansion for Fourier Laplace type integrals, which looks like e to the minus lambda f of 0 times lambda to the power of d half times the square root of 2 pi to the power of d divided by det a times the exponential of minus a half kt a to the minus 1 times k divided by lambda. All right. So what did this is for lambda to infinity, and we'll see what happens if we go with k to infinity then. So when we apply this to the curly p case, you'll see what happens. Okay. So what did you do? We started from a theorem using Laplace's method in order to evaluate the kind of integral we started out from, right? Integral e to the minus lambda f times g of x. And we applied this now to Fourier Laplace type integrals. And the result is this. And now we take a break. What do you want a break? Yes. 5 minutes? Geht für große K, ja.
we were discussing to apply the saddle point approximation for particle interaction. Now this is a free form, the free version. But now I'm thinking like then our g function, which is like
Go on. All right, let's restart then. So some of you ask, do we now have to take lambda large or k large or whatever? You'll see. Because now, as we are going to apply this, so far we have only assumed that both lambda and k are large. Now we are going to identify them. Because now we want to apply this result to this integral here. And the first thing you notice is that, as you probably remember, the limit of f of r for r to 0 is minus sigma 1 squared divided by 3. So the exponential prefactor that we have here exactly cancels this. And this simple statement rules out lots of statements that you find in the literature saying that in the Seldovich approximation you will have exponential damping of structures. This is not the case. It looks like, but then you see from the asymptotic expansion that the exponential factor is exactly cancelled away. Very, very important insight already. Now I'm going to drop the exponential prefactor altogether, right? Because it's gone. All right. Then I'm identifying lambda equals t times k. Okay? Squared. So now we are going to apply this to our curly P power spectrum. Lambda equals tk squared. And now, of course, the problem is gone, right? Because as you send k to infinity, you also send lambda to infinity and vice versa. Then I can assure you that f has a global minimum that r equals 0. Next thing we need to look at is that this expansion of f, or this representation of f, and for that I will have to evaluate the k transpose times CPP times k. As you evaluate CPP, you're free to orient the vector k as you like. And I'm going to rotate the coordinate system such that the vector k that I'm choosing here points into the z direction. I can arbitrarily do this. So then I find that f of r is given by minus integral k times k prime squared. This comes from multiplying these two wave vectors here with the k primes in this matrix. Times p psi of k prime times e to the power of I k prime times r. And I need to integrate this over all k prime. And remember our notation, right? This is k prime squared dk prime d phi d mu divided by 2 pi to the power of 3. That's our notation for Fourier back transform. Okay. Now if I orient k such that it points into the z direction, then I can write this as kz prime squared times k squared. And I can factor the k square out and cancel it. So in other words, I can write f of r is minus integral kz square, sorry, kz prime squared, e psi of k prime e to the I k prime times r. Now let me write instead ekx prime eky prime ekz prime divided by 2 pi q. Sorry, it was not a smart move. Let's stick with polar coordinates. All right. Now we need the Hessian. So the Hessian consists of taking derivatives with respect to components of the R. And each of these derivatives will bring down an I times k of that particular component. So in other words, if I want to know the Hessian at R equals 0, I will take a derivative with respect to R and tensorially multiply it with another derivative with respect to R in order to get this matrix. I will get a factor of I squared, which will cancel the minus 1. So I will get integral k prime is the angle between k prime and z-axis. Then I will get k prime tensorially multiplied with k prime. Need a matrix here. Then I get p psi of k prime, and then I can stop because now I've taken the derivatives. Now I can set r equals 0. So now the phase factor just becomes 1. And the coordinate system, again, remember, is fixed such that the external wave vector k is oriented along the z-axis of the coordinate system. Okay. Now what's this like here? K prime square dk prime d mu d phi divided by 2 pi q. Okay. Now what's this like? By symmetry, this whole matrix will be diagonal. And we have one preferred direction, that's the z direction. The other two directions by rotational symmetry about the z-axis must be equal. So I know that I need to be able to write this as this thing here. So I need to evaluate now two of these numbers, A11 and A33. If you don't believe that, well, just write this matrix here into angular components or into angular expressions and carry out the phi integral, and then you see that this is true here. Okay, now what is A11? A11 is what happens if I insert kx prime and kx prime here. So this is integral 2 pi cube k prime to the power of 2 4 6 mu squared. Now if I take the x components, each of them will contain sine theta and not a cosine theta. So taken together, they will contain a sine square theta or a 1 minus cosine theta squared or 1 minus mu squared. Then for x and x, the two x components, I will get another factor of cosine squared phi that I need to integrate over phi. So then I have keep psi of k prime, now dk prime, d mu, d phi. Okay, the easiest is the integral over the cosine square phi from 0 to 2 pi. That gives you a factor of pi. So that is pi divided by 2 pi cubed. And the phi integration is gone. Now the next one is the integration over the mu squared. This gives you a factor of mu cubed divided by 3. And this gives you a factor of mu to the power of 5 divided by 5. So evaluating this in the boundaries minus 1 to 1 gives you 2/3 minus 5/3. So that's 10 minus 6/15. So that's 4/15. So times 4 over 15. We have done a very, very similar calculation already once. Right? All right, and what is left over is k prime to the power of 6 times the power spectrum of the velocity potential. But k prime to the power of 4 times the power spectrum of the velocity potential is the power spectrum of density fluctuations because of Poisson's equation. So I could right away write this as k prime squared and p delta here. And if I have an integral over k prime squared times p delta dk, this is one of the moments of the power spectrum that we already introduced. Namely, this is 2 pi squared times sigma 1 squared. All right, now let's take stock of what we have. We have 2 times 4 times pi squared times pi. That's 8 pi cubed. How nice! It's gone. So what is left is just sigma 1 squared divided by 15. All right. What would change if we evaluated A33 instead of A11 here? Well, the only thing that would change is that this factor 1 minus mu squared would change to a factor mu to the 4th. So then we would get by integration a factor of 2 over 5 instead of 2 over 15, or 4 over 15. And this cosine square would be gone. So the integral over phi would give 2 pi instead of pi. So the only thing that would change is that this would be sigma 1 squared divided by 5 instead of sigma 1 squared divided by 15. Okay, so we have the matrix A is sigma 1 squared divided by 15, diagonal matrix 1, 1, 3. And now, of course, the determinant and inverting it and so on is not a miracle anymore. So the inverse is 15 over sigma 1 squared, 1 diagonal 1, 1, 1/3. And the determinant is 3 times sigma 1 squared divided by 15 to the power of 3. And you see the determinant is positive. Very good. So our Hessian is positive definite. Lovely. Now we have everything together in order to apply the above result to our power spectrum, and then we are going to stop. And we need to remember one more thing, right? We have already chosen the orientation of our k vector. So k transpose times a to the minus 1 times k transpose is just k square divided by a33. Okay? No more, no less. All right, so I know k transpose a to the minus 1 times k. This is k square 15 over sigma 1 square divided by 3. In other words, 5 over sigma 1 square times k square. Now you see that if you replace lambda by k square t square, that all k dependence in the exponential is gone. So you see that I now can't write curly p anymore because the exponential prefactor is gone. No, yes, I can, of course. The exponential prefactor is just going away. Then we have the asymptotic expansion of the integral, and except for the exponential prefactor, this is all we have. So this is 1 over k square t square to the power of 3/2 square root 2 pi to the power of 3. Now 1 over that a. Remember that a was sigma 1 squared divided by 15 cubed times 3. So this is divided by 3 sigma 1 to the power of 6 times 15 to the power of 3. This needs cosmetics, I understand. But let's move on. Then we have exponential of -1/2. And as I said, k transpose times a to the minus 1 times k transpose is just this expression here. So this is -5/2. The k square cancels out. And we have sigma 1 squared t squared. There is no k dependence anymore. And you see, you can write this as 1 over k to the third power. And I'm going to pull the t to the power of 3, or t squared to the power of 3/2 into that. And then it will be a factor of t to the power of 6. So then I have 2 pi times 15. So 30 pi to the power of 3 divided by 3 sigma 1 squared t squared to the power of 3 times exponential -5 divided by 2 sigma 1 squared t squared. This is a most remarkable result, which is not due to me, of course, but due to our PhD student, Sarah Conrad. And what I've shown you is one of the main contents of her PhD thesis. Right? What this says is the following. Number one, we already had this. Contrary to many claims in the literature, there is no exponential damping in the Soldovich approximation. Not even on the smallest scale. Number two, whatever you do, you will end up with a nonlinear power spectrum that goes like k to the -3, and the power of -3 is only set by the number of space dimensions. There is no influence of cosmology. There is no influence of the type of dark matter that you're looking at. So this means that the asymptotic behavior of our nonlinear structures, at least in the free case, is set by k to the -3, where 3 is the number of spatial dimensions, universally. You can derive some more things, or you can look at some more things here. Maybe we should discuss this next time. So first of all, it's not the time that controls our time coordinate, right? Linear growth factor. It's not the time that controls structure growth, but it's the product of sigma 1 times time. This could be called structure formation time, and it is, again, a dimensionless time coordinate which dictates how structure formation proceeds. In the lecture notes, we have abbreviated this as sigma. Then you can see that the power spectrum, or the amplitude of the power spectrum, is essentially e to the minus sigma divided by sigma to the power of 3/2 times numbers. So the amplitude will go through a maximum. And the maximum is easily found. All right, so let's search for that. Right? So this will be this looks weird. This is because this is wrong. And you don't say anything. Okay, wrong. We need this. So this is this. So you can factor out a lot of things, but once you do, what remains is, and since this is supposed to be zero for a maximum, you find that at sigma equals 3/2, the nonlinear power spectrum will go through its maximum amplitude, or the asymptotic tail will go through its maximum amplitude. And then you can, of course, also insert this here and calculate the height of this amplitude. And this is universal. It does not depend on your cosmological model. It does not depend on the type of dark matter. It only depends on the sigma 8 moment. Sorry, nonsense. The sigma 1 moment, at one of the moments of the initial power spectrum. That's it. The shape of the initial power spectrum and the expansion function of the cosmic background and so on just don't matter. This is a very important lesson. And this illustrates another aspect of universality in cosmic structural measure. Yes? Yes. Yes, that's right. So you see that with increasing time, this is getting ever smaller, so this exponential goes to 0, but this is decreasing with time. So why is that? This is because in the Soldovich approximation, particles meet and happily form structures, and then they pass and destroy the same structures. And only if we include interactions, for example, with perturbation theory or something else, we can counter the decay of structure or the decay of this amplitude. Yes? No, it seems that the asymptotic behavior of the interaction term is becoming K independent, but I can't prove this yet. And it's very sad that I can't prove this yet. But it seems that as you include more and more density fluctuation modes into the interaction term, you integrate over all K up to a limit, and this integral becomes K independent, and then it will just multiply the amplitude but not change the shape. And then this K to the minus 3 behavior would pertain also for nonlinear interaction. But this is approximately where we are. I can't say more than that right now, just because I don't know.
But we have not known yet that R is the zero.
True, that's for you to work out. The best way of doing this is to use this representation. Okay, sorry for running over time, but I thought this was important. I'm going to leave without questions because I have to go to the train station, but we meet again next week, okay? Thank you very much.